All right, so now we're going to transform specific functions. No longer general, we want to know what these graphs look like. These graphs on your paper are all the functions we're going to learn about this school year, plus some. So it's not all of them, sorry. But it's a lot of the basic ones, and it's their parent functions. So the parent function is the most basic version of that function. That means there's nothing added, nothing subtracted, no multiplication, no negatives, nothing. This is as straightforward of that type of problem as you're going to get. We've got linear, we've got absolute value, that makes a v. Our cubic function looks like half a quadratic and then half upside down. Square root function, it's a sideways parabola, but only one half of it. Quadratic, there's your parabola. Rational, and then exponential. And we're going to do less with our rational and exponentials today. So we're not getting quite there yet, but we will eventually. And so you still want to know what they look like. So let's transform specific functions. First, we're going to describe the transformation, and then we're going to draw the graphs. So we have to know how to describe the transformations, and there's nothing really crazy going on here, right? We did a lot of this last class. So let's just go through and describe all of our transformations. Why not? So let's look at this one. We've got -5 on the inside. That's a right 5 and down 5. For B, we've got the negative on the inside and the outside. So those are that's two different reflections, right? So this is reflection in the X and Y axis. And then this +2 moves it up 2. And it doesn't even matter what the graph is, right? We're doing the transformation regardless. Here, there's a negative on the outside because the function is x cubed. So the negative is a reflection in the x-axis. And then this is moving up 1 because of the +1. You know it's outside because there's not an inside. In order for it to be a reflection in the y-axis, it would look like this. But that's not what we have here, right? Here we have the negative first, so that's the difference. That's how you know the difference. Same thing here. For D, that's a reflection in the x-axis, again. Because it's not inside of the square root, okay? It would look like this if it was a reflection on the y-axis. Then the -5, because that's on the inside, that means we're moving right 5, because that is inside the radical. You see how it cuts off right there. And then that +2 is an up 2. This 2 right here for part E, that's also on the outside. So we have a vertical dilation by 2, and then it's moving down 3. So this will be a good opportunity for you to see what a vertical dilation is. In F, you see how there's an inside because there are parentheses. That's your inside. So that's your horizontal. That's your horizontal dilation, and we describe it by its reciprocal. So we're going to take 2 over 1 and we're going to flip it, so it's actually by 1/2, and then down 2. So let's see what these graphs would look like. Now, in order to do that, we want to look back at our parent functions. So the first one we're dealing with is a quadratic because it's x squared. That's your indicator. That square, right? That exponent. It normally looks like a u. So it normally looks like this. Now, this is not the final answer. I'm just drawing it so you have a frame of reference. Okay, that's what it normally looks like. But it's moving to the right 5 and down 5. So I'm going to move this vertex to the right 1, 2, 3, 4, 5, and then down 1, 2, 3, 4, 5. And that's where my vertex is now. It's not reflected, so it's not flipped anywhere. That's my new graph, the green graph. That's the new one. For a reflection, for an absolute value function in part B, that's what we have. And we've already looked at these a little bit. They're v's. So they start as 0, 0. So our parent function, I'm just going to probably going to draw all of my parent functions for you so you can see what we're looking at. It's a reflection on the x and the y-axis. So if it's a reflection on the y-axis, it's just going to flip. But in the case of an absolute value function, it actually doesn't change the graph. You would flip it, and it's symmetric about the y-axis, so it doesn't do anything. Now, the reflection about the x-axis, that does change something. So I'm going to put an intermediate step just so you can see the reflection in the x-axis. So I'll go from top to bottom. Then we're moving that up 2. So let me show the movement up 2 of that. So we're going to be up here, and the green graph, hope you're listening, that is the answer. Okay, so I'm just going to remove the intermediate step so you don't get confused, but that's why that happened. For a cubic function, let me just tell you, a cubic function looks like this. This is cubic because that's a 3 on the exponent. It looks like a parabola, but it's half up and half down instead of both up. Okay, now this is going to get a reflection in the x-axis and a movement up 1, so there's going to be another intermediate step. The reflection in the x-axis is going to cause it to go down on the right and up on the left because that's reflecting. And then we're going to move it up 1. So the center, instead of being at 0, 0, that it's going to be at 0, 1. So we're going to have the same graph as the red line, but shift it up 1. So we'll get rid of the red, and that's the answer. A square root function. A square root function in part D normally looks like this. It's a little swoosh to the right, starting at 0, 0. Now this time, again, we're going to have a reflection in the x-axis, so it's going to flip over the x-axis. So I'm going to have an intermediate step, and it's going to look like this. Kind of looks like a sideways parabola, but it's just that red portion, not the red and the black portion. Then we're moving it right 5 and up 2. So we're going to go over 1, 2, 3, 4, 5, up 2. I'm going to draw that same graph going down, so it's actually right there. And we'll get rid of the red one. Now for part E, just trust me when I say, the way that I figured it out is by taking numbers and plugging them in. So I highly advise you just make a table of values. But a vertical dilation, essentially it stretches it up. So it's going to be thinner than your standard parabola. Now this is a quadratic function because again, squared. So it's normally going to look like this. But because this is vertically dilated by 2, then instead of it being at the point 1, 1, right here, if I plug 1 in, I actually get the point 1, 2. So it's pulling it up. And instead of 2, 4, I'm going to get 2, 8. Because it's pulling that up also. So it's going to look something more like this. It's much thinner. It's going to grow much faster. And then we're pulling that down. So it's going to go down 3. So let me draw this to my best of my ability. Still nice and thin. And that green line is the final answer. For your horizontal dilation, it actually does something very similar to what your vertical dilation does. Again, I'm just taking numbers and plugging them in. So it's cubic, so it normally looks like this. But I'm moving it down 2, so let me do that first. So we're going to go down 2, boom. And then instead of it being up 1 over 1, if I plug in 1, 2 times 1 cubed gives me 8. Because 2 times 1 is 2, cubed is 8. So I'm going to go up 8. And that's how much thinner it is. So it's really, really, really skinny. But that's the graph. Now, it's going to cut me off in a second. So there's going to be a really, really short extra video. But that was necessary. You needed to know what that looked like. Okay, so one more video. It'll take like 2 minutes.